So this is a data configuration we encountered before, and we cannot separate the two groups of data points by a linear function. But let's still put a wide avenue between the two groups of data points. Now there are some data points, there are two green points, are on the wrong side of their dashed line. So we're going to formulate our problem this way, and for data points on the correct side of their dashed lines, we know they satisfy yi, beta xi plus beta 0 is strictly bigger or equal to 1. But for the two green dots, they are on the wrong side, we're going to adjust the bar on the right. Instead of asking them to satisfy this to be bigger than 1, we're just going to introduce a slack variable 1 minus xi I. So they only need to be bigger than 1 minus some number. Here xi I is always bigger or equal to 0. So the xi i's can be regarded as the error we made on the ith data point. If data are on the correct side, then we know the xi I can be this is satisfied by setting xi I to be 0. But if they're on the wrong side, then the xi I will be non-negative. So the final objective function becomes a summation of two terms. The first term is reciprocally related with margin, so we want to minimize it. And then gamma is a tuning parameter, which is the price we want to pay for getting 1 unit of error. So some of the xi i's will be regarded as error. And they're subject to the following constraint, and the inequality constraint now with the slack variables, and all the slack variables have to be non-negative. Here are we aim to minimize this objective function, and now the arguments is beta, the slope beta 0, and also the xi 1 through xi n. So this is still a convex optimization problem where the objective function is quadratic and the constraints are all linear constraints. Now the number of constraints get doubled. We have 2n constraints because for every observation we have 2 constraints. Because this is a convex optimization problem, and we still have this nice property, any local optimal is going to be a global optimal, and then the 3 components are equivalent: the KKT conditions, the primal, and the dual problem. So let's work out the 3 components. This seems to be a very scary slide, but please bear with me. You're going to find a lot of terms will be cancelled, and we're going to deal with a dual problem, which is almost the same as the one for hard margin. First, the primal problem. This is an objective function. Gamma is a tuning parameter and will be specified by the user. In practice, you're going to find out we can choose it by cross-validation. So the parameters for the primal problem will be beta, p-dimensional slope, beta 0, intercept, and xi 1 to xi n. And then we're going to write down the Lagrangian function. So the Lagrangian function has 2 sets of parameters in blue and red. So the blue parameters are the one from the primal. And then we have 2 sets of multiple Lagrangian multipliers. Lambda 1 to n is for this constraint, and eta 1 to n is for this constraint, this set of constraints. So the Lagrangian multipliers are in red. Then let's just write out. Write the Lagrangian function. This is the original objective function from the primal, and then minus Lagrangian multiplier times the corresponding constraints, and then another set of a Lagrangian multiplier times the corresponding constraint. So this is a Lagrangian function. And then we can merge some terms. So we're going to keep the first term, and then this term becomes this term, and the -1 and there's another minus sign in front, so it becomes sum of lambda I. And the remaining terms are all involve psi I. So for each psi I, we have gamma, we have minus lambda I, minus eta I. So we put them together is gamma minus lambda I minus eta I. So this is a Lagrangian function. And you're going to find out the first three terms. You can pause the video and check what is Lagrangian function for the hard margin formulation. The first three terms are exactly the same as the original, as the Lagrangian function for hard margin. And then the last term, as you're going to find out by the KKT condition, this is actually 0, so we can cancel it. Okay, so this is a Lagrangian function, and we keep everything. And then let's work out the KKT conditions. And the KKT conditions, there are four groups of the conditions. Let's explain them one by one. So for the first group of conditions, they are the Lagrangian function. We take derivative respect to each of the three blue parameters and set them to 0. So this is the derivative of the Lagrangian respect to beta, derivative respect to beta 0. So they are the same as a hard margin problem because beta only appear here and here, and beta 0. And the last equality is the derivative of the Lagrangian respect to psi I. So you can find out this term actually going to be 0. So the first group of KKT will be derivative of Lagrangian with respect to the arguments or the parameter from the primal, and we set them to be 0. Then the second group of KKT conditions will be, require all the Lagrangian parameters, Lagrangian multipliers to be non-negative. So all the lambda i's, all the eta i's have to be bigger or equal to 0. And then the third group of KKT conditions where we just restate the constraints from the primal, which is this one and this one. And then the last group of conditions will be the complementarity conditions. That means lambda I and the corresponding constraints, because lambda I is the Lagrangian multiplier for this constraint. They cannot be non-zero simultaneously. And then similarly, eta I and the corresponding constraint psi I, they cannot be non-zero simultaneously. So we are done with the KKT conditions. And next, let's work with the dual problem. So the dual problem is basically just a Lagrangian function, but now we're going to use some equalities we get from the KKT to get rid of all those blue parameters, and then they change into, instead of doing minimum, we're going to do max respect to those lambda 1 to n and eta 1 to n. And you're going to find out these three terms, because they're the same as a hard margin and the equality is the same as a hard margin. So this expression from the dual is the same as a hard margin. And only difference is now the lambda i's. Previously, we only have lambda i's to be bigger or equal to 0. But now, because of this condition, there is an upper bound for lambda I, because lambda I plus eta I will be equal to gamma, and lambda I and eta I are positive, so the lambda I should be less than gamma. So this is a dual problem, and you're going to find out, although we're supposed to maximize the dual respect to both lambda I and eta i's, but eta I never appear in the expression, so the maximization is only over lambda 1 through lambda n. So follow the same path and framework we did for the hard margin. We're going to optimize the dual problem and solve lambda 1 through lambda n. They are the Lagrangian multipliers, and you're going to find out some of the lambda i's, only a small fraction of this lambda I is going to be non-zero. They are known as the support vectors. Once we know those lambda i's, we can use this formula to solve beta. And then one of this formula is going to be exactly equality without even psi I, because there are at least some points are on the dashed lines. then we can use that equality to solve beta 0, and then we are done. Now let's look at what are the data points that are going to be support vectors. And support vector is going to be data points with non-zero lambda i's. So let's look at the data points. Let's divide them into three groups. The first group will be the data points. They are on the correct side of the dashed line. So for those data points, because you're going to find out they are going to satisfy we're going to find out what's inside the bracket going to be non-negative, because automatically for those points there's no psi I going to be 0, and then yi times the linear function will be strictly bigger than 1. So the expression inside the bracket going to be non-zero, then their lambda i's will be forced to be 0. So they cannot be support vectors. Okay, so if you're on the correct side of the dashed lines, and similar to our discussion in the hard margin case, they cannot be support vectors. So this is the first group. The second group will be data points. They are on the dashed lines. So for those data points, similar to the argument we had for the hard margin case, we don't know their lambda i's, and they could be, at least we know the lambda i's may not be 0. So they could be potential support vectors. The third group of data points will be the data points. They are on the wrong side of the dashed lines. Now you're going to find out for those data points, they're going to have non-zero psi I, because we have to make this equality to be true. So for the data points on the wrong side of the dashed lines, the psi i's, which are going to contribute to the arrow, will be non-zero. That means their eta I is going to be 0. That also means their lambda I is going to be gammas, will be non-zero. So they are going to be the support vectors. So in summary, for this soft margin formulation, again, we go through the framework to solve the dual, and then go back to solve the beta and beta 0. And then beta and beta 0 will only depend on those support vectors, and support vectors will be data points on the dashed lines, and also data points on the wrong side of the dashed lines. And for this particular configuration, we're going to have 4 support vectors. Okay, one additional parameter in the soft margin formulation is this gamma. So gamma is the price we pay for having data points on the wrong side of the dashed line. And you're going to find out, even for separable configurations, we may want to consider this soft margin formulation. For example, in these two pictures, the location of the data points are exactly the same. On the left, we go with the hard margin formulation, and we just try to squeeze an avenue between the two groups of data points. And you can tell it is a pretty narrow avenue. But on the right-hand side, we're going to place a wide avenue. And yes, some data points are going to be on the wrong side, but eventually we try to minimize the objective function, which is combine combine two goals. One is to max the margin, another is to minimize the error. So it depends on how we are going to choose our gamma, and then we may favor the right hand side instead of the left hand side. So let's look at the role of gamma. Gamma apparently is going to be a number from 0 to infinity. If we increase gamma, for example, if gamma is going to be infinity, then that means we won't allow any non-zero slack variables. That means, for the left hand, for this case, we have to go with the left choice, the choice on the left, which is sort of the same as the hard margin formulation. So when gamma is equal to infinity, we're back to the hard margin formulation. in no data will be allowed on the wrong side and no points and on this avenue. So if data are not separable, that means there will be no solution. And so in general, if we increase our gamma, and then we going to pay more price for having error. That means our avenue going to be narrower. That means less number of support vectors, and it actually means a more complicated model and actually the tendency to overfit. And why is that? And you're gonna find we can understand the role of gamma and by looking at an alternative formulation of the SoftMargin formulation. So this is our primal formulation. And you're going to find out that can be equivalently written this way. Here, we're going to think about our fx, which is just a linear function. So fx is just a function on x. Here is a linear function, and the f will depend on beta and beta 0. So the inequalities, you can find out if yi times fxi is strictly bigger than 1, that means 1 minus this yi times fxi going to be negative. And then xi I going to be 0, as we mentioned before. If the data are on the correct side of the line, the xi are going to be 0. And on the other hand, if the inner product is less, not the inner product, just yi times fxi is less than 1, and that means 1 minus yi times fx will be just xi I. So if we put them together, you're going to find out the xi I basically is 1 minus yi fxi, for this number. We're going to take only the positive side, meaning this expression is going to be 0 if this difference is negative, which is case 1. Otherwise, just going to be the difference, which is case 2. Then you're going to find out, then we can use this one to replace xi I, and then also, so this, and also move and sort of a, and instead of using gamma, we use a eta. So those two expressions are equivalent, and the gamma for the primal and the nu for this equation 6, they are reciprocally related. Now, what's interesting about this equation 6 is basically back to our loss plus penalty framework. So what is a loss? The loss is the first one, which is called the hinge loss. Remember, our yi is going to be either 1 or minus 1. And fxi, now you can view the fxi is a classification function we try to learn, which here is a linear function. Once we fit a learn a classification function f, we basically just look at the sign of fx. If it's positive, then we classify the corresponding y to be 1, otherwise it's just minus 1. So ideally you want yi times fxi just to be positive. That means their sign are gray. But we want something more than just to have the same sign. If their product is a number less than 1, and we still feel the evidence is not strong, we want them to be the same sign, but also if yi is positive 1, we want our fxi to be some number bigger than 1. And yi is negative 1, we want our fxi to be a negative number with a magnitude also bigger than 1. So our loss function is defined to be 1 minus this. So you're going to find out, and sometimes people call this as the margin of this classifier and f. So here's a plot and product. So here's a plot of the loss function, and the x coordinate basically represent y minus fx. So again, y is labeled as 1 or minus 1. Our fx is a classification function we learn. It's going to output a real number, but then we're going to classify based on the sign of f. So we look at the product. If the product is very positive, that means not only my fx going to get the same sign as y, and it is also give us a very strong evidence because fx is very large, or when y is 1, or sort of very, very negative when y is minus 1. So the so-called hinge loss is basically this blue curve. Now, what's the ordinary 0-1 misclassification error loss, where the usual loss is the black line, which is a so-called 0-1 loss, because our loss will be 1 if y does not agree with f, does not agree with the sign of f. But that's the same as just look at the sign of the product of y times f. If it's positive, no loss, flat. And if it's negative, you get loss 1. So the black line is ordinary 0-1 loss. And you can find out the log likelihood or square error loss and take a different form. So SVM can be viewed as just the ordinary loss plus penalty framework, where we just use hinge loss, we measure it over n observations, and our function f is going to be a linear function with parameter beta and a beta 0, and we add a range penalty over beta. So you can see the gamma and the nu are reciprocally related. So this is why we said, well, when gamma is getting larger, that means the penalty is smaller, so the model is getting more complex, and we tend to the resulting model tend to overfit the data.